Okay, let's go over the test. Problem one, the ball is tossed straight up. Its height is given by this equation. Now, if you graph this, even though the ball is going straight up, as time passes, the height will get higher and higher and higher, and then it'll come back down. And at time 0, it has a y-intercept of 8. So it starts off up at 8, wherever 8 is. I'll make it here. And then it's a negative 4.9 t squared. So that's an upside down parabola. And the 20t is making it go up. The 8 starting up there, and then it comes back down. Now it's going straight up and down. But this graph is recording how high it gets as time passes. So the time is passing, but the ball is going straight up and down. So as time is going along, it starts here and then comes down. Okay, so just so you understand what's going on with the equation. Now, the number in front of the t squared makes it a parabola that's upside down. And the number also is, since you're on Earth and gravity is what's causing it to come back down, even though it's thrown up, that number on Earth is either negative 4.9 or negative 16. If it's negative 4.9, that's half of the acceleration due to gravity in the metric system. Acceleration due to gravity is negative 9.8 meters per second faster every second. So it's speeding up in the negative direction 9 meters per second faster every second. Now, if it was a negative 16 here, t squared, then the negative 16 is half of the acceleration due to gravity in the English system. So negative 32 feet per second faster every second. That's the acceleration at the surface of the Earth. Every second it goes 32 feet faster in the downward direction. That's why the negative. Every second. 32 feet per second faster every second versus 9.8 feet per second faster every second. So if you see an equation with a negative 16t squared, the units are feet and seconds. If you see a negative 4.9 t squared, then you know the units for time is seconds. In both cases, the time is in seconds. And the height is either meters or feet. In this case, 4.9 says the height is in meters. So there's the answer to part A. Now to find out how high it is, now the height is going to be in meters, so my units are going to be meters. After 0.7 seconds, several people wrote the equation correct. You need to do negative 4.9 times 0.7 squared plus 20 times 0.7 plus 8. Several people wrote that and still got the answer incorrect. So I'm going to do this on the calculator, and I'm also going to do it on Desmos, I think. The thing you got to watch out for is you can't take the 4.9 times the 0.7 first and then square. Order of operations say square this 0.7, then take it times negative 4.9. Now, if I were to type this out in steps, I would go 0.7. Okay, let me show you the keystrokes here. Let's see. Yeah, I'll leave it here. I think you can do the 0.7, but I can push the x squared button right there and get squared, and that's 0.49 times negative 0.49 for 4.9, and I get, for this first term, negative 2.401. But if I were doing this on a calculator, I would type the whole thing in. Now, if you're doing it on a phone calculator, you have to do it in parts. You do that part and do that part and then add them up. But here we go. Negative 4.9, parenthesis, 0.7, close parenthesis, squared. Oop, get it where you can see. Plus 20 times 0.7 plus 8. And I get 19.599. And that would be meters. So if it started at 8, 19.599 would be somewhere about that high. And it happens at 0.7 seconds, because that's what we put in for the time, and we got a height of 19.599. Now, if I want to put in 1.2, I can go back to here, but I'm going to show you something, an easier way to enter numbers into an equation. So I'm going to go to y equal, I'm going to clear all these, and I'm going to type in the equation. Negative 4.9, and I know it says t squared, but on the calculator it likes x, and x is right here, so I can just go x squared. There's the square button right here, plus 20x, so x is my t, plus 8. And then if you table set to the independent variable being on ask, then when I go to the table by doing second graph, and clear, go up here, delete and delete, I can enter the numbers I want to put into the equation. So I can put in 0.7, and it gives me the 19.599. And that would be meters. Now I'm going to put in 1.2, and it gives me 24.944. So I'm doing negative 4.9 times 1.2 squared plus 20 times 1.2 seconds plus 8, and I'm getting 24.944 meters. Okay? Now I can do the same thing on Desmos. So I've got Desmos over here. Let's see if I can get the camera to point at it. And I can type in H shift parenthesis of x. It doesn't like t as the variable, it likes x, equals negative 4.9 x, and to get squared you can come down to the bottom. I can't see that on the screen. Down on the corner down here there's a little keyboard thing. If I click on it, it gives me the square, so I click there. And there's that upside down parabola. And then we have to go plus 20x, so that moved it, and then plus 8, and now you can see it starts going up at 8, and it keeps going up higher. You can see it go up. As time passes, it goes up and comes back down. But it's in actuality going straight up and down. But as time passes, the height is on this graph goes like that. And if I click on the gear here, I can ask it to make this a table. And in this table, I can get rid of these numbers that are in there and put in my own numbers, like I wanted to know what it was at 0.7. And it tells me 15.99 or 19.599. And if I wanted to know at 1.2, it'll tell me 24.944. And it puts dots at those places. There's the 0.7, and here's the 1.2. Okay? And this one's undefined because it's just a minus, so take that out of there. And I can put another thing. There's 0, it's at 8. At 1, it's 23.1. There, that's this one. And at 2, it's 28.4, which is really close to the top. Now, the top is a little bit off from there. So that's the maximum height it gets to. And it happens at 2.041 seconds, and it's at a height of 28.04. Okay, so that's how you can use Desmos to get those answers to those parts. Now, let's continue on. It says, now find out when the height is, get this to be in the right place. There we go. When the height is 12. So on the calculator, I can do that. I can sit here and guess at the time that it's at 12 and keep messing around on this table, making guesses. Let's like 1, it's too high. 0.5, still too high. 0.3, still too high. 0.2, little low. 0.21, 0.22, a little bit too much. So it's in between 0.21 and 0.22. I can keep guessing like that, but I can also go to my y equals and make another graph of the y height of 12. Just type in 12. Okay, now if I had zoom, let's stop here. Zoom 6. It goes off the screen and down, and you can't see the top. So to fix that, you go to Window, and we're looking for times between -10 and 10. The heights, we're going from -10 meters to +10 meters. Well, this goes higher than 10 meters. So maybe I want to make this be 50 meters. Is that high enough to see the top? Yeah, it doesn't get up to 50 meters. And the second equation I typed in was 12. So here's how high it is as time passes. And we want to know when it's 12. So I just drew a line at 12. And where they intersect, the time will be the time it takes to get up to there, from 8 up to there. And there'll be another time when it's coming back down. Now to find those on the calculator, we use the calculate. It's above trace. So I go second, calculate. And I want the intersection of the blue equation, enter, and the red equation, enter. And my guess is pretty close to 0. And it says, nope, 0.2109 rounded. So at time equal to 0.2109, and then it's again at 12 over here. So I can go second, calculate the intersection between that blue equation, enter, that red equation, enter, and I gotta get closer to here or it'll keep giving me that answer. So I need to move over near that spot, and that's my guess. And it says the answer is 3.871. It's 3.871 approximately. Those are in seconds. So it gets to a height of 12 pretty soon after it's thrown, 2/10 of a second later, and then 3.8 seconds after it was thrown, it gets back to 12. So explain the meaning of what you just found. This is the time it takes to get to a height of 12 meters. In 0.21 seconds, the ball gets up to 12 meters high, and at 3.87 seconds, the ball returns to 12 meters high on its way down. Now, you can figure out this number, the height at 1.2, which was this, and the height at this with that. You can subtract them and you can figure out the change in height. But what I'm asking for the meaning of this, and it's the change in the height of the ball from 0.7 seconds to 1.2 seconds. So this calculation will tell us the change, the difference in the heights of the ball between 0.7 seconds and 1.2 seconds. That's kind of what I'm looking for here. Now, to find these times in Desmos, we do pretty much the same thing. We've got the graph here, and I would type in a new equation, y equals 12, and didn't like y equals 12. We did h of x, so let's go h of x equals 12. Why is it not showing? Oh, wait a minute. There it is. I wasn't up to where. There's 12. So it probably did y equals 12. Anyway, here's the 12. And to find those times, you just click on the point, and there's the 0.21 seconds. It's at a height of 12. And at 3.871, it's at a height of 12. You just click on the graph where they intersect. So finding intersection on Desmos is a little bit easier than doing it on a calculator. Okay. All right, we're ready to do number 2. Now, some of you had a little bit of trouble reading this graph. So you want to look where you can see the units the best. And over here, they're kind of faded. But over here, you can see this is a definite line here, there's one there, and halfway would be between. Looks like it's right on this line. If you can barely see the line there, you can see the line there, and this is right in the middle. So 1, 2, 3, 4, 5. Each of these must be 10 miles per hour, 20 miles per hour, 30 miles per hour, 40 miles per hour, and 50 miles per hour. So this is the speed, the velocity. And horizontally, these are time in hours. So this is 1 hour, 2 hours, 3 hours, 4 hours. Okay. So this says find the speed at 3 hours of the blue car. Now, which one of these is the blue? Blue is the horizontal line. You may want to write that right on your graph. And so that stays the same height, 30, all the way through. So the velocity at 3 hours is the same as 2 hours, the same as 1 hour, same at the start. It's 30 miles per hour. That's what the vertical units are. Now, acceleration is the average rate of change of velocity. So I asked for the acceleration of the red car, that's the other line, at 2 hours. So it's going to be the slope of this line at 2. Well, the slope of this line is the same all the way through because it's a straight line. So all I have to do is find 2 nice points. And this one looks like it's at not 20, 30, or 30, but 25. So at time 0, it's at 25 miles per hour. That's what the red car is doing. And the next nicest place is clear out here at 5 hours. It's going 30 miles per hour. So if I call this Y2 and Y1, I got 30 miles per hour minus 25 miles per hour. That's Y2 minus Y1 over X2, 5 hours minus 0 hours. And so the units of my answers are miles per hour per hour. 30 minus 25 is 5 miles per hour faster every 5 hours. So if you want to, you can reduce that to 1 mile per hour faster every hour. So there's the units, and this is the acceleration. Acceleration is how much the speed changes and for how much time it takes to make that speed change. And it's the slope of the velocity graph. Now, this says find the distance for the blue car. The blue car is the one that's going straight, so it's going constantly 30 miles every hour. And I asked you to find it after 2 hours. So the first hour, it would go 30 miles, and the next hour, it would go another 30 miles. It's going 30 miles per hour, and we have to take it times the number of hours, which was 2 hours. And they cancel the hours, and we get 60 miles that it goes. And now, if the cars start at the same place and the red one's going slower, 25 miles per hour, than the blue one at 30 miles per hour, then the blue car is going to get ahead of the red car because it's going faster. And at 5 hours, the red car finally gets going the same speed as the blue car, but the blue has been going faster all the way up until then, so it's got a substantial lead. And to lose that lead, it's going to take, since the difference in the speeds is pretty much the same, it's going to take the same amount of time for it to catch up. If it took 5 hours of getting behind, it's going to take 5 hours to catch up. So the red car is still behind at 7 hours. It's tied at 10 hours. So at 7 hours, the blue car is still ahead. If you want, you can add the red car would catch up at 10 hours. Okay, let's go to 3. Now, most people did 3 pretty well. But there are a few people that still haven't figured out. Notice that there are 16 gaps. 1, 2, 3, 4, 5, 6. We're counting the gaps, not the marks. There's 16 gaps to make an inch in this of the tiny marks gaps, and so each one is a 1/16 of an inch. So if I start here and count gaps, I got 1 gap, 2, 3, 4, 5, 6, 7, 8th gap, 9th gap, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18 jumps of size 1/16. So it's 18/16 inches. Now, it turns out that it comes out even, which means it could be done in every pair. So there'd be 1 pair of gaps, 2, 3, 4, 5, 6, 7, 8, 9 pairs, and each pair is 2/16 or 1/8. So I could call it 9/8 inches, or 1 1/8, or 1 2/16. But any of those answers that I just mentioned is the correct answer for 3. Number 4. I have a piece of paper that is 14 inches this way and 20 inches this way. And if I fold up equal amounts on this side and this side, that's going to make the width of the bottom 14 minus however much I folded up. And if they're both the same, it's going to be the same amount subtracted twice. So the width would be 14 minus the amount I'm folding up is 1 13/16, and I'm going to fold it up on both sides, so it's going to be reduced by 1 13/16 twice. Now I could write that as 14 minus 2 times 1 13/16, and I could actually figure out what 2 times 1 13/16 is and say it's 14 minus, let's see, 2 times 1 is 2, and 13/16 times 2 is 26/16, which I can take 16/16 out of this and make this 3 16 sixteenths is one more, and I'd have 10 sixteenths left. Or I could call 10 sixteenths 5/8, so 3 5/8. So it could be 14 minus 3 5/8. Depends on what your comfort with fractions are. And if I take 3 off of 14, I get 11. And if I take another 5/8 off, 11 minus 5/8 is going to be 10 3/8, because I'm taking 11, borrowing 1, which is 8/8, and I'm subtracting another 3/8, and that makes 8/8 minus 3/8 is 5/8, and I get 10 5/8 from 11 minus 5/8, and that's inches. And the length would be 20, and since I'm folding up the same amount on all sides, so this is also 1 3/16 supposedly, and 13/16, and 1 13/16 on this side, the length of 20 inches is getting reduced by 1 13/16 on this side and 1 13/16 on this side. So it's 20 minus 2 times 20 minus 1 13/16 twice, or that would be 20 minus 2 times 1 13/16, which is 20 minus 3 5/8, because 13/16 twice is 3 5/8. If I take away the 3, I get 17. If I borrow 1 more, that's 8/8. I get 16. 8/8 minus 5/8 is 3/8. So that's the length, the 20 inches minus 2 1 3/16. My width is 14 minus 1 13/16 on each side. The height is just however high I folded it, which is 1 13/16 inches. And the volume is length times width times height. So it's 16 3/8 times 10 3/8 times 1 13/16. Now, a few of you that doing the test converted those. You said 16 plus 3 divided by 8 is 16.375, and 10.375, and 1 plus 13 divided by 16 is 1.8125. Those would be decimal values for those, and you can multiply those numbers. But I'm going to show you how to type this in on a calculator. So parenthesis, 16 plus 3 divided by 8. 16 3/8. You do 16 plus the 3/8 more. Then to do the 10 3/8, parenthesis, 10 plus 3 divided by 8. And then the 1 13/16 is parenthesis 1 plus 13 divided by 16. And this comes out to be, in decimal, 307.93 rounding. And this was inches times inches, which is inches cubed. An inch by an inch by an inch deep makes a cube, and that's why it's called cubic inches. So you could write inches cubed or cubic inches. So I'm looking for units. So I'm inches that way, inches in that measurement, and cubic inches is the volume. Now, instead of folding it up by 1 13/16, what if we want to know the maximum volume we can get? Well, then we got to let the amount we fold up be a variable. So instead of folding up 1 13/16, I'm going to call the amount that I fold up x. And if I do it there, it's going to be x on the other side. And so my width is now going to be 14, the total width of the paper, minus x on this side and minus x on this side. So it's going to be 14 minus twice however much I fold up. And the length is going to be 20 minus x on each end, or 20 minus 2 x's. And the height of the box is going to be straight up just a single x. That's the height of the box. Okay? So the volume, as a function of how much I fold up, is 20 inches minus 2x, however much I fold up on each side, and the 14 minus how much I fold up on each side, so that's 2 times the x, and the height will be just whatever I fold up. This would model the volume. If I took this equation and put in 1 13/16, I should get this volume here. So I'm going to show you how to do that on a calculator. So I'm going to clear this, clear that one, and go up here and type in parenthesis 20 minus 2x, close parenthesis, open parenthesis, 14 minus 2x, close parenthesis, and then the height is just x. The length minus x on each side, the width minus x on each side, times the height, which is just x. And if I have that table set like I do to independent on table set, independent is an ask, I can go to the table and I can type in whatever size I want. So I'm going to delete all the sizes I've put in here, and I'm going to put in 1 plus 13 divided by 16, and it'll tell me if I use that size, I'm going to get 307.93. Okay? But I want to know what x gives the max. Well, we could guess here until we see which one gives us the most, but we can also go zoom 6 to graph, and the graph goes up, goes off the screen, comes back down, and then goes back up. Now to find the max, it must be somewhere in here because it's going up. To see that high up, the amount I fold up is the x's in the equation, but the y is the volume, and the volume gets to be at least 300. So I might want to make the maximum volume be 400, and maybe marking every 50. 50, 100, 150, 200 graph. So now it's 50, 100, 150, 200, 250, 300, 300. It's a little less than 350, it looks like. And I want to know what that maximum height is. Now you can use trace, but it won't give it to you exactly. It gives you pretty close, 388. If I go to second calculate, it says you can find the maximum. And what it wants to know is, where do we want to look for it? Now, if I had a graph that goes top, bottom, has several maximums, I have to tell it, look for the one between here and here, or from here to here, or from wherever they're at. So you can do that by arrowing, but I like to type it in. I'm looking for one that's somewhere between 0 and 6. So I'm going to type in, look, the left side is maybe 0. The right side is probably less than 6. So it's drawn lines that it's going to look between there for a max. It wants me to help it get a good start, and so I'm going to say 3. And it says, no, you should fold up 2.703, and you'll get 339. Notice that's a little bit more than what I got from tracing. So what X yields the maximum volume? 2.704. 2.704 inches folded up. That's more than 1 13/16. That's how much I should fold up. And it gives us a volume that's 339.013. And that would be, the volume is inches by inches by inches, inches cubed. I want the units. Okay? So now let's do that on Desmos. So I'm going to type this equation in and try to find these two. So over here, we're going to show you my computer screen, get it straight up and down if I can. The camera is not always cooperative. That's fairly good. You can see it here. So I got to get rid of this equation and that table and that value, and I want to type in v of x equals, and it was parenthesis 20 minus 2 times the amount I fold up, parentheses, in the other direction, the width, 14 minus 2 times the amount I fold up, because it's taken off of both sides and both lengths, and then the height is just the amount I fold up. And we get the same kind of graph here. Now I can just, if you got a, there you can squeeze it on your fingers, but I'm using my mouse and rolling out. Now I need to go up here and find the maximum. And it happens, if I click on that point, it happens to 2.704, and I get 339.013 for the volume. Okay? So that's how you can do it on Desmos. Now, I want to go back to the x-axis, because the next question I ask is, what is the meaning of these x-intercepts? That's an x-intercept. It crosses the x-axis. It crosses at 7, 0 and at 10, 0. So the x-intercepts are fold up 0, I end up with 0 volume. Fold up 7, I end up with 0 volume. And fold up 10, I get 0 volume. Those are the 3 x-intercepts. And I want you to tell me what they mean relative to the actual activity. So back here, if the amount I folded up was 0, in other words, I didn't fold anything up, I wouldn't have a box. And so the box would have no volume, because x equals 0 is no fold. So the box would have no height. So it would have no N-O, volume. At x equal, the next x-intercept was, let's go on this one. The next intercept was there. To find that on the calculator, I go second, calculate the 0. That's somewhere between 3 and 8. So I got to press left bound 3-ish, right bound 8-ish. Notice it marks where I'm going to go between. And it looks like if that's 8, it looks like it's about 7. So I'm going to guess 7, enter, and it says, yes, 7, the volume is 0. So at x equals 7, remember that's inches. Now, the paper was 14 inches wide. So if I fold up 7 and fold up 7, there would be no width left. And if the box has no width, it has no volume. That's half of 14 inches, so no width left to my box, so there's no volume. That's why it's a x-intercept. Y is 0. The volume is 0. And the last one happens to be off the screen. I need to look over here further. So I go to my window and I want to look at bigger x's. Let's go to 15 inches and then push graph. And there it goes up, down, and up. There's one there. And you probably can guess what it is, but it's somewhere between 8 and 12. So I'm going to go second, calculate the 0 that's between 8, enter, 12, enter. I'm going to guess 10, and it says, yes, 10. 10 inches is half of the 20. If I fold up 10 this way and 10 this way, that leaves no length left. Uses up all the length. This is half of 20 inches, which would leave me with no length. And with no length, I'm going to get no volume. Remember, the volume is length times width times height. If any one of those is 0, we're going to get no volume. The height is 0, the width is 0, and the length is 0. So that's what it means, what the x-intercepts and how they're related to the box. Okay? I want this relationship here. That's why I'm getting no volume. It's not enough to just say they cause the volume to be 0. Yeah, it's the volume 0, but why? Relate it to the box. Now the domain. Well, the x's, the only sizes we can fold up are somewhere between folding nothing and folding 7, because that's half of 14. We can't fold any more than 7 on the width. So the domain is somewhere between 0 and half of 14, which is 7. And technically, I could fold 0 and I could fold 17. Well, 0, I can't. That's no fold, but I can imagine that. Now, if you wanted to write 0 to 7 are the only ones that make sense to make a box, that's fine. So I accept either one of those answers for this. The range, the volumes that I get out, are going to be somewhere between 0, if I fold 0, and to 339.013 inches cubed. If you want to use parentheses there, that's fine too. Okay? That's page 2, and I think I'm going to stop there and save this and then start another video for the last pages.